Okay, so just a little bit of housekeeping. As I said, this webinar is being recorded. Please keep yourself muted until we get to the Q&A section, which will be after the presentations. If you have any questions as we're going along, if you could put those in the chat and we will get to those at the end, or just keep them and we'll ask you to raise your hand once we get to that section, please. So just to explain who I am and who we all are, I am Morven, I'm project manager at TownRock Energy, and TownRock has been the industry lead for this Galleries to Calories R&D project, and we are a geothermal consultancy based in Edinburgh. Galleries to Calories is a £2.6 million funded pilot project that we have been working on for the last 3 years with partners in Scotland, the USA and Ireland. And we're using this to demonstrate for the first time the use of legacy mine workings to store heat and to transport this, and ultimately looking to see if this can be used to heat homes and businesses. I'm not going to go into detail here on it now because my colleagues are going to go into a lot more detail in this session and the ones to come. Just to explain who the partners are that have been involved. So as I said, TownRock was the industry lead, the academic lead was the University of Edinburgh, and particularly Professor Chris McDermott, who has the initial idea for this project. So big thanks to Chris for having the initial idea and putting all the work in to get to where we are now. Thank you obviously to all of our funders as well, that you can see there that made this project possible. Here's just a little diagram showing the concept that we were working on. I'll let you have a look at that, but we will go into that in a lot more detail. And here is the final outcome, the borehole that we drilled, and you can hear more about that at the Work Package 3 presentation, which is in 2 weeks' time. So I hope you're going to be signing up for that one as well. And now I will pass on to my colleagues Leah and Sam, who are going to go through the details of their work package.
Thanks, Morven. Okay, hopefully that has come through now. So thanks so much everyone for coming. Today we are going to be presenting on Work Package 8. So this was looking at the techno-economic feasibility of the geobattery concept. So using those flooded mines for storage and transport of data center waste heat. So myself and Sam will be kind of sharing the presentation today, so I will kick off. So just a bit, this is a bit laggy. Okay, so just a bit of an overview before we get started. So I'll go first into a bit of the background on Galleries to Calories, the project itself, and then more details on Work Package 8 that we'll talk about today. We'll then move on to talk about supply and demand assessment. So as part of this work package, kind of key things that we needed to do were to work out how much waste heat can we get from the data center, and what is the heat demand in the area around the data center. So we'll cover that, and then the bulk of the presentation today will be on the techno-economic modelling that we performed and kind of the journey that we took through that process. So just before I get started, sorry, I'm waiting for the slide to change. There we go. Okay. So yeah, just before we go into the background, I would like to show this image to explain what the galleries in the name of this project is. So these are abandoned mines exposed at surface. And what you can see where my mouse is now is kind of remaining what we call pillars of coal. So when they're excavating coal, they leave these pillars to hold up the roof. And in between where we have these stacks or pillars of coal, you can see that we have these spaces, void spaces, and these are what we call our galleries. So when these are flooded in the subsurface, they're flooded with water, and we can use that water for our heat storage and transport. So as Marvin already said, the project is a 2.6 million 4-year project involving a number of partners. And we said the aim is to demonstrate that for the first time, the use of these mine workings, our galleries, to store and transport data center waste heat. And the heat is, of course, the calories, which is where the name comes from. So why is this important? At the moment, data centers use about 3% of global electricity, and of course, this is set to rise, exponentially as we see the growth of AI. And actually, cooling is a huge portion of this already. So cooling accounts for up to 50% of that electrical use. This means that for data centers, there's a really high cost of cooling, but it also means that for us, there's a really large potential waste heat source there. So based on this is where the geobattery concept came from. So the idea is that we use the mine workings. So we take relatively cool water from the mines and we use that to remove heat, that waste heat from our data center. We then re-inject the warmed water back into the mines and we create this warm plume in the surface. And then we can take advantage of that plume. So downstream, we can then start to abstract that warmed water and use it in our heat network. And this is the geobattery concept. So what we did for work package 8 was we wanted to look at the techno-economic feasibility. And to do that, we looked at a specific case study at the University of Edinburgh. So at the University of Edinburgh Easterbush campus, so we're kind of just south of the city of Edinburgh, we have the Advanced Computing Facility, or ACF, which you can see here. So this is the data centre that we used in our case study. As you can see in the surrounding area, there are a number of towns that are potential heat demands. And of course, really importantly, we have a lot of mine workings in the vicinity of the ACF. So you can see all these purple areas are where we have mine workings in the subsurface with 3 different collieries in the nearby area. So going on then to think about the supply and demand assessment. So the first thing that we looked at was how much waste heat do we have available? So we looked at the ACF and the existing infrastructure there in order to determine that. So the graph that you can see on the right-hand side, this is from Archer 2, which is one of the computing rooms within the ACF. And you can see that over a 3-year period, the utilisation of that computing facility is really high, so kind of sitting around 90 to 100% across that 3-year period. And that's because the ACF is a nationally important computing facility. Now, that is really good news for us because it means that we've got lots of waste heat available. So we have basically 6 megawatts of waste heat available 24/7 all year round, and that's at about a temperature of 32 degrees. So just a couple of things to mention, which we'll kind of come back to later on, is that at the moment, because the ACF is located in Scotland, where it's quite cool for most of the year, the ACF can actually use atmospheric free cooling for about 3/4 of the year. So that is a very efficient and a very cheap form of cooling. However, we know that the ACF is going to be expanding in future to a potentially much bigger data centre, so up to maybe 30 megawatts. And that will significantly reduce the potential that we have for free cooling. So we'll just bear that in mind for future. So now we know how much waste heat that we have available. The next step was to have a look and see where are there potential heat networks in the vicinity of the ACF. So to do this, we used an established methodology which uses 2 main parameters. So the first is anchor loads. So these are buildings that have really high, stable, reliable heat demand throughout the year. So things like hospitals, supermarkets, schools, for example. And you can see the anchor loads that identified. These are the kind of red blobs that you see on the map on the right-hand side. The second parameter that we use is the linear heat density. So this is a really commonly used parameter when we talk about heat networks. And what that allows us to do in this case is create these kind of bubbles around each of our individual buildings with heat demand. And effectively where those bubbles overlap is where we have potentially financially viable heat networks. So what we see in the vicinity of the ACF then is that we've got these two heat network clusters. So we've got one in the Easterbush area down here. So that's just next to the ACF, which again you can see in this blue diamond. So we've got the Easterbush network, and then we have another potential network up in Lone Head. And you can see from the table that the demands of those two networks are quite different. So the Lone Head network is much bigger and has a much higher demand.
Yeah, I do.
So we've looked at the waste heat that we have available, and we've identified some potential heat networks. The next step was to start to think about, okay, if we're injecting heat at the ACF, where is that heat going in the subsurface? Now, as Morven mentioned earlier, this has been performed as part of other work packages, for example, work package 3. So we'll kind of touch on the essentials that we need for the understanding here, but of course, do tune into the other lunch and learns if you are interested in learning more about those work packages. So as I said earlier, there are extensive mine workings adjacent to the ACF, and there was lots of work done in these other work packages that informs the subsurface assessment here. So this is another photo of the rig drilling the borehole, and you can see on the left here some of the core that we obtained there. And you can see, areas that we've identified as mine workings on that core. Now for us, this was really, really important because it allowed us to get some key parameters that were used in the modelling. So we found out the presence and the depth of the various mine workings in the area. We found out the mine water temperature, which is about 16 degrees at the bottom of the borehole, and also the groundwater level, which is relatively deep at 104 metres below the ground level. That also allowed us to determine some hydrogeological properties as well. So all of these parameters, they were used then to inform subsurface modelling. So this was performed by our colleagues at the University of Edinburgh. So Alejandro, who I think is on the call, he did a huge amount of work on this modelling. So what we were doing with that modelling was simulating the injection of waste heat near to the ACF, and then seeing how that's kind of stored and transported in the subsurface. And you can see on the map on the right-hand side here, this is the kind of extent of that geobattery, basically that warm plume in the subsurface, which you can see is moving kind of to the north and east in the direction of groundwater flow. So when we first saw the results of these modellings, this modelling, you can see that the plume is actually relatively limited in its extent. So we looked at size and the shape of the plume, and we said, okay, it looks like it would be really good if we can look at our heat network in Easterbush to utilise that waste heat. So this was the focus of the early techno-economic modelling that we did. So I will now go on to that. So just before I dive into the different scenarios that we looked at, I want to give you a bit of an overview of what we did. So of course here the main thing that we're interested in is the geobattery itself. We want to find out about the economic feasibility of that. However, we thought it would be useful to model a few different scenarios so that we can compare them. So I'll talk about each of these in more detail, but we looked at mine water cooling only, a direct connection between the data centre and the heat network, and then we move on to our geobattery scenario, and then Sam will come on to talk about the hybrid geobattery later on. So for each of these scenarios, we performed a conceptual system design. So basically, we looked at all of the components that we need for our mine water systems. So you can see a diagram on the right here. We considered things like our boreholes, their depths. We also needed to think about the surface plant, so heat exchangers, heat pumps, circulating pumps, and then of course our kind of pipework and distribution around our heat network. So doing this, we could then get our system capex, so that upfront cost, and the operating cost throughout the lifetime of the system, and that allowed us to determine the levelized cost of cooling and the levelized cost of heating, which we can then use to compare each of the different scenarios. So starting off with the first case. So this is mine water cooling only. So you can see in the diagram here, we're using that kind of relatively cool mine water in order to take away the waste heat from the data centre. But we're not doing anything with that waste heat in this case, so we're just storing that in the subsurface. So in order to do that, we need 3 abstraction boreholes and 3 discharge boreholes. What we initially proposed was that these would be located quite close to the ACF, so you can see them in this field here. However, when we did the modelling of this, what we saw was that actually, because the boreholes are located quite close together and we're injecting a lot of heat into the subsurface, we actually start to see thermal feedback in the abstraction boreholes. So basically, we start to abstract warmer water, which obviously impacts the cooling efficiency quite significantly. So what we had to do for the mine water cooling case was actually have our abstraction and discharge boreholes located in separate collieries. So you can see now that we don't have any thermal feedback within our abstraction boreholes, so we can maintain the cooling efficiency throughout the project lifetime. Now, looking at that on a map, you can see that what this means is that our boreholes, our discharge boreholes here, are now quite far away from the ACF, which obviously has implications in terms of the pumping in order to get our mine water to and from these boreholes. And when we start to think then about the cost of this system, you can see that mine water cooling is more expensive than the business as usual case at the ACF right now. So it is partly due to the costs associated with pumping, but the main reason for this is, as I said earlier, at the moment the ACF can do atmospheric free cooling for about 75% of the year, which is a really cheap cost for cooling. So moving on to case 2 then, this is just a direct connection between the data centre and the heat network. So you can see we're not involving the mines in this scenario at all. So no mine water system means that we don't need any boreholes. So that does reduce the upfront capital cost. Of course, we still have the cost of the pipework and the connections that we can see on the right. However, the main consideration when we think about this direct waste heat connection is that the waste heat supply and the heat network demand aren't exactly linked. So the ACF, we said, has pretty much a constant heat output all year, so that's about 6 megawatts. However, of course, the heat network demand changes throughout the year. So what we see is that we can do that direct waste heat connection for a portion of the year. However, during winter, the ACF cannot meet that peak demand, so we need quite significant peaking plant use. On the other hand, in summer, we can't shed all of the waste heat to the heat network, So that means that the ACF requires a different method of cooling in the summer months. So looking at the levelized costs, so starting off with the levelized cost of cooling, you can see that actually the direct connection is cheaper than the business as usual here. And that's because for this modelling, we assume that the district heat network operator is taking on a lot of the costs associated with the cooling infrastructure because they're getting effectively free waste heat. So that means the cost of cooling is low, which is good. However, you can see the cost of heating is more expensive than the business as usual, which we've assumed is gas boilers. And that's because we have, things like this significant peaking plant use that is an expensive method of heating. So now we come to the geobattery. So as I said before, we are taking the waste heat from the data centre, injecting it into the subsurface to create this warm plume, and we can then abstract from that warm plume for our heat network. So in this case, we need 3 abstraction and 3 discharge boreholes for each system. So for our mine water cooling system and our mine water heating system. The really good thing about this configuration is that our boreholes can be located closer together because we have abstraction downstream. It means we don't see that same issue with thermal feedback as we saw for the cooling only option. So taking a look at the modelling, you can see that actually it's really advantageous to have this geobattery because the abstraction boreholes for our district heat network, they can take advantage of that really hot area within the thermal plume, so they're getting elevated temperatures in the subsurface. So effectively, our geobattery is acting as a really big thermal store, so we can store all of that waste heat within the winter months, within the summer months, sorry, and then we can use it during winter. So taking a look at the levelized cost of cooling and heating, you can see that these are actually both more expensive than the business as usual for the geobattery. And that's because we have both a higher upfront cost associated with drilling, what is quite a lot of boreholes in this case, and also the operational costs associated with the pumping to and from the boreholes and to and from obviously the mine water level. So to kind of give a conclusion on where we got to at this stage of the initial work, is that when we look at mine water cooling only, these systems really look uneconomic when we compare it to the business as usual. And that's, as I said, primarily because we have such high use of atmospheric free cooling in Scotland. However, as I mentioned, we know the ACF is going to expand in future, which could limit the use of free cooling. So if we take a look now at this graph, if we had to do mechanical cooling all year round, we see that actually the mine water systems look much more appealing in those cases. For the direct connection, we saw that looked quite good, and that was mainly because our data centre is really close to that heat network in this case. And then finally, we saw that our geobattery was more expensive than the business as usual. And that is quite particular to the challenging subsurface conditions that we saw at this site. So we had a deep water level, which obviously has a big impact on those pumping costs from your mine water level. We had low groundwater flow rates and a relatively high mine water temperature. That being said, if we compare it to other low carbon solutions like the air source that you can see on the bottom graph there, we can see it is still more economic than those alternatives. So at this point, we decided that we know the geobattery is more expensive than business as usual, partly because we need such a large number of wells. That has implications in terms of both the CapEx and the OpEx costs. Additionally, when we were trying to work out where all those wells would go, it actually becomes quite tricky to work out where they can go at surface when you've got houses and other buildings. So we decided as a next step, we would look at this hybrid or mine water thermal energy storage, MTES, case, which uses both the direct connections and the mines to reduce the well numbers. The second point there, we saw that the Easterbush heat network, while it was well located kind of just next to the plume, the sparse demand there was actually perhaps not the best for returning investment. So we decided that for the next step, we'd actually look at the Lone Head heat network instead. And then the final point, last summer, the ACF was confirmed as the home of the UK's next national supercomputer. As I said, that's likely to be a 30+ megawatt data centre, so a huge increase in the heat supply. So the final point that we wanted to investigate then was to look at the impact of that increased waste heat supply. So that was the kind of where we went next. So I'll pass over to Sam to take you through those scenarios.
Yeah, so thanks, Leah. So yeah, as Leah mentioned, our next steps were to look at the Lone Heads network. And yeah, I'll just give you a brief run through of what the results look like for that. So if we first look at that direct waste heat connection, which is that kind of counterfactual where we're not considering mines. Similarly, there's no wells needing drilled, so that reduces the capex. But you can still see here that you can see the heat demand in green and the data center output in pink, and you can see although they're better matched in Easterbush, they're still not particularly well matched. So again, in yellow, we can use the connection for a lot of the time, but there's still a very big requirement on peaking plant. And actually, because the peak demand of this network is larger, you end up using a lot more peaking plant, which obviously is going to impact the cost. And then conversely, in the summer as well, when the heat can't be shed to the network, we need to find alternative methods to cool the data centers, so air conditioning and mechanical cooling, which is energy intensive. And yeah, that's kind of translated here into the higher levelized cost of heat for that direct connection. And again, similarly, the cooling costs are low because we're assuming the heat network operator takes on the cost of the cooling infrastructure in return for free heat. So this is the geobattery scenario again, but for the Lone Head network this time. And pretty similar story in that we needed 3 abstraction and 3 discharge boreholes for each system. And again, we locate them close together because you actually want that interaction of the heat plume to be picked up by the heat network. And similarly again, there's a reduced requirement on peaking plant, and you can see that that translates into a levelized cost of heat that for this larger network is actually a bit closer to the gas levelized cost of heat there. So we're getting better, but could we do even better? And the answer is yes, and that's some combination of those 2 connections there. This is the MTES, as Leah mentioned, the mine thermal energy system. And this is probably best explained via this graph again. So the idea is that when you can, you use that surface heat connection. And then in these like shoulder seasons, when the demand is higher than what the ACF can provide, you then tap into that mine water resource. That mine water resource is recharged in the summer months. So when the data center has waste heat in the summer and it can't be shed to the network because it's warm and no one wants heating in the summer, you dump that into the mines, and that enhances the recharge of the mine aquifer. So, oh yeah, and there's only a very minimal requirement for peaking plant there. So you've got a much better balance of supply and demand. And you can see there, because we're only using the mines in the shoulder season, you need fewer boreholes. And actually, yeah, we only need 4 in total, so 2 warm and 2 cold, which has good implications for the cost. And you can see there the thermal modelling as well. We've kind of got those distinct hot and cold plumes being created as we dump and exchange heat from the subsurface. And yet, so in terms of levelized cost, because we're needing to drill fewer boreholes, pump them less, this all translates into a levelized cost that's actually is competitive with gas. You can see there it's actually beating gas, which is great. So if we look at them all together, we can see that both, if we consider this larger lone head network, although it's further away, because the heat demand is better matched, actually both the mine water heating options, so that's the geobattery and this kind of hybrid solution, actually look pretty good for the lone head. And that hybrid solution, which I mentioned last, is actually, it's more favourable here because, as I said, we need fewer wells and that's lower pumping costs. And that's significant here because the water level, if you recall, is 104 metres below ground level. So that's a big power input required to pump the water up through that head. And the direct connection, as we mentioned, because of that big reliance on peaking plant, that's what's causing that to be so much higher. So if we now look at the cooling, as we've said, we've assumed that the levelized cost of cooling, it's low because we've assumed that the heat network operator absorbs most of the cooling costs in exchange for free heat. And that's probably a good first pass assumption. The details of this would obviously be thrashed out in later stages of the project, but I mean, that's models used elsewhere, so that's probably a reasonable assumption for now. And yeah, you can see I've included here, we've got the business as usual, which is the cooling as they currently do, based largely on atmospheric free cooling. And I've also included here this higher one, which is that first scenario that Leah showed, which was if the data center has to pay for the mine water cooling, it doesn't add up so much in Scotland, because obviously it's cooler and it's cheaper to just use atmospheric free cooling. So yeah, I guess it's crucial to note that these results are specific to this site in the Lothians and that subsurface configuration. So the next step really was to ask, could the geobattery be even better elsewhere? So to start answering this, we looked at other coal fields. So where the subsurface configuration is more favourable. So where we are in the Lothians, we've got very steeply dipping mine workings, which is perhaps not the best for allowing that plume to spread. So we kind of looked at where there might be better configuration, like flatter mine workings elsewhere in the country. And then the other aspect, of course, is this hotter climate. So where outside of Scotland, where we may not be able to do free cooling for large portions of the year, that is where it might be more viable to turn to these mine water cooling options. So this is an example here of a coal field in the UK that looks quite favourable, and that's in the northeast of England, where there's already quite a lot of momentum around mine water heating with the Gateshead schemes, and it's also happens to have quite a few data centres and population overlap. And as we know, there's a lot of mine workings in the coal measures there, and the strata are actually quite flat lying, which allows that plume to spread out, so that was good. And then we've also got pretty good constraints on water levels, because there's a lot of legacy mine activity there, a lot of MRA activity to control this, to measure mine water levels. And so then to take like a wider perspective, we then started thinking, well, actually in very hot climates and arid climates, especially where perhaps there's more constraint on water use, we're starting to think, well, actually, maybe for that cooling only scheme that didn't perhaps look as financially viable in Scotland, if you imagine in perhaps parts of the US and the tropics and stuff, where that cooling via the atmosphere is just not an option, and there's also a lot of mines elsewhere in these parts of the world, then these ideas have huge potential elsewhere. So yeah, I think while we did a lot of work on Easter Bush and Scotland, this work is very exciting to sort of generalize across the world, and that's where it's going to have real potential for cooling only schemes. Finally, we looked at sort of the larger ACF, and yeah, as that waste heat supply increases, we need to obviously increase proportionally the amount of heat injection capacity, and that starts to exceed how much you can take out of the ground from a heat network. So this slide here is just kind of showing the effect of having an ever larger data center, and it's kind of saying that there is an upper limit to all of this. The ground can only take so much heat before you end up with thermal feedback and sort of thermally short-circuiting your system. And that's especially pertinent here, where I was mentioning we've got steeply dipping line workings, and that plume's not able to spread out as much as other sites. And so, yeah, it's crucial to note that these results here are specific to this site, and modelling elsewhere would be required to sort of demonstrate the exact thermal configuration, the thermal plume extent there. So I think this is our last slide, but it's, yeah, just to say that our main takeaways from all this is that the mine thermal energy storage and that kind of hybrid solution, rather than just having a geothermal mine water scheme on its own and a data center in isolation, using them together in a smart way is kind of the most economic way of providing simultaneous heating and cooling. And yeah, the economic feasibility of these systems is strongly dependent on that kind of balance of the heat supply from your data center or your other heat source, waste heat source, and of course the demand profile of your heat demands in your heat network. And of course the subsurface configuration of the mines is crucial, as we've just been saying. So yeah, obviously, yeah, this is going to require at each site we need to do a specific analysis, because we know that mines are different everywhere. But yeah, there's huge potential to use this kind of concept more widely across the UK, but also, yeah, in those kind of hotter, drier, more arid regions, as I mentioned, around the world. So yeah, just to say a massive thank you to everyone who's helped with this this work package over the past couple of years, and I think that's it. Thank you for listening, and yeah, happy to open the floor to questions. So yeah, thank you.
Thank you very much, Leah and Sam. If you have any questions, you're welcome to raise your hand or put something in the chat, and we'll happily try and answer them anyway. If you just want to unmute yourself, if you're the first one to ask something, please go ahead. Oh, yeah, Ali, you want to unmute yourself.
Yeah, hi everyone. Thank you. That was a brilliant, excellent presentation. I've seen some of these results. The only thing I wanted to ask is the capital cost that you included, and you said that it's mostly involved with the heat network, right? The operator. That includes the pipelines, the wells, and the heat exchangers. So in all these cases where the mine water and or the data center and the heat network are connected, those costs are assigned to the heat network operator, right?
Yeah, exactly. So yeah, the heat network operator takes on the capital costs and also the pumping operational costs for all of this. So the data center is a kind of standalone party that's just dumping its waste heat, and then the heat network operator or some third party deals with it after the exhaust point from the data center. Yeah.
Perfect. Great. Thanks.
Any other questions from anybody? We managed to answer everything in the presentation.
there's anything you think of afterwards, feel free to let us know.
Yeah, absolutely. The email address is there,
Yeah.
hello@townrock.com. So if you do have any questions, please put them in an email, send them over to us, and I can make sure it gets to the right person and you get an answer. But if there are no other questions, then I think I'll bring this to an end. And just to say thank you so much for joining. I hope you found it interesting, useful. I hope you will join for some of our other presentations that are happening over the coming months. They're all available on our Eventbrite, and I'll also be promoting them on LinkedIn. So please do sign up, join us for those, share the word with colleagues as well. We'd love to see you to tell you more about the work that we've been doing. So thank you very much, everybody.
Thank you.
Thanks,
Thank
everyone.
you.
Brilliant work. Thank you.
Thanks very much. Great.